You can see I'm getting there. So what I'm doing here is instead of thinking of these I'm putting sort of a distribution on these distributions in a way. Because I'm saying that I've got an unknown. Think of x0 as a parameter. Okay, it's where I pick the mean value for the reward. Okay, and so let's write this down. So my reward, if u of t is 1, then the expectation of r of t, or ut minus 1. And there's a conflict here. It's because I'm trying to I'm sorry. Yeah. T plus 1 t. I need to do this, as you'll see as well. I have to, a slight conflict with this. I'm sorry. And again, it's because of allergy attacks. Otherwise, this would be a little cleaner. I apologize. There's a one-step delay in this model. No big deal. I pick out the first, if u of t equals 1, I pick out the first component of this. The state doesn't change as a parameter. It's not really a state. So this is exactly the expectation of that. I'm assuming the expectation of this is 0 because I'm trying to force this into the LQG setting from last lecture. So I assume that that x of 0 was Gaussian somewhere. Let's assume the same thing for W. So make this all Gaussian and everything. Now, so here's something that that's usually not taught in these courses, and it should be, is that I'm allowed to have a state space model like this. It's completely degenerate, first of all, here. There's no noise here. The only randomness in the state is the initial distribution, initial condition. And I'm allowed to let my observation equation, so this is really now y. Within parentheses. That's I'm basically observing the reward as I would as I'm pulling the arms in a slot machine. I'm allowed to have my observation equation have coefficients that depend on my observations from the past. And the common filter still goes ahead. It still works. Yep.
And C is your...
So C of t, I'm using the notation from LQG theory for the linear models. Before you had an A, a B, and a C, in the LQG model, and you were able to come up with a conditional distribution. Well, it turns out that if you have a wacky time-varying observation matrix, this, row vector in this case, which actually depends on your input, it all goes through. You can still apply the common filter, no problem at all. Okay. All right. So what would you do with this now? So now I can apply the common filter. So two questions you could ask. One is, what does this thing look like? Well, you can write down the common filter equations. It's kind of messy, but you can do it. So and secondly, what do I do with it? So we do know that ut star is equal to some phi star of a yt sigma hat t and sigma t. Damn it, that's still true. Because x hat t and sigma t determine the conditional distribution. It's still conditionally Gaussian. That's still true. Even when you've got this thing here, you still, the conditional distribution of the state is Gaussian in these conditions. You know? But does anybody have a guess on what this might look like? I know what most people would say if they weren't scared, you know, but. Yeah, I mean, because we want it, you know, the better arm is the one where this is bigger, right? You know, we'd like to always be able to choose, you know, if this expectation is bigger than the other expectation, we'd like to always pull ut equals 1 every time. Yeah. So what would you do? You know, you've got all this information, you've got the, we'd like to know this mean. If we know this mean, we're done. You know? Oh, wait a second, Jesus Christ. Ah. I don't even want to know the mean. It's not the mean we'd like to know. Sorry, everybody, just trying to think. Damn. God, I'm going to have to come up with a correction next lecture, otherwise we'll waste too much time. There's a mistake here, and it's too hard to explain, but it's just, like I said, I have not been feeling well. We can't assume, I said, how do I say this? Turn the thing away. No, I'm going to have to prepare this next lecture, okay? Because I just realized there's a mistake in this formulation that's too hard to try to clean up now. Because if I told you I knew that, then I do know that, and I know everything, and so I know what to do. That's not what it is. I can't assume I know x1 bar. So you know, I've got to correct this. But let me just put it this way. You can set this up properly, and I'll clarify it next time. What you end up with getting, I'm going to erase this. What you end up getting is that x hat I of t is approximately just an average of a capital T. Wait a second. Let's say, I'm sorry, x hat I. This game. All right. And that should not be t. That should be, I'm going to call this, n sub t of I. Okay, there's surely a typo here, but let's check it out. So, Aditya, you were going to say? Oh, because of the fact that I put a delay in the system, yeah. Which I really regret. So, yeah. I put a delay, unfortunately, in this example, and I was just trying to force it into a particular setting. So, it's not exactly that. You end up getting something having to do with the uncertainty at the initial there's something to do with the uncertainty in X. Instead of 1 over ni of t, you'll get a constant here. But it's approximately just a Monte Carlo average. Okay, so you can go check that out. If you plug in the Kalman filter, you get that. So we have these things here. You're basically averaging the reward that I received when I pulled arm 1, and I average the reward I received when I pulled arm 2. And what would you do with that information?
You pull the one with a higher reward.
Yeah, so one policy, the optimistic policy, well, I'll just put a 1 here. So there's a name for that. That's the optimistic policy. And that is certainty equivalence, you know. That's like the separation principle or plug-in policy. You know, let's call it that, the plug-in policy. So, you know, if you knew the average reward under action 1 was bigger than the average reward in action 2, you would always do this. So those hats were really the means. That's what you would do. All right. So is this it? Can we go home?
Because machine won 5 times in a row, so it probably won't win again.
No, well, no, it's all IID. I mean, it's all IID. And that's how people think in Las Vegas. So I see what you mean.
The opposite of an optimistic policy is, oh, well, it won't continue. So I'll pull the other one.
Yeah. Well, the thing is, we can't. Let's put our voodoo from Las Vegas aside. What's wrong with this policy? And maybe I misunderstood you, because that sounded like voodoo. Like when people pull an arm, I won too much now. I've used up my luck on this machine.
If they say they have the same mean, and you do this, 1,000 times, and x1
No, don't change the problem. One's better than the other. Let's assume Let's assume one's better than the other. Is this going to work or not?
Well, but again, you may have gotten lucky and hit a spot where you got, you're flipping an unfair coin.
Yeah, no, but remember, we're going to take t pretty large, capital T pretty large. So will we maximize this reward with that policy? Of course, there could be transients where things screw up, but if we run this thing long enough, well, is it going to work?
I say yes. Well, I think it's no, but I don't see no. Just back to the exploitation versus exploitation.
Well, no, just the thing is, can we see any problems with this criterion, trying to maximize this criterion using that strategy? Maybe. But I don't know, maybe. I think as long as they're both random, I think you've got a problem. Yeah. And it is, it does go back to the original point. Am I learning?
Well, if you pulled them both, if t is really large, you pull them both a lot.
Well, I guess maybe what's not clear is this is all online. Every day I'm trying out new treatments on patients. Every day I'm making new contracts with billboard companies. I'm doing this every day. Observe the past, The next day I make new contracts with, or whatever. So this is an online process. Every day I go in, or every hour or whatever, I go in and pull another arm.
But the slot machines aren't going to change. The probabilities aren't going to change.
No. Well, that's the assumption this model we're going to make. That's right. In this particular case, the reward is, given by this. We'll assume that's IID. And so the statistics don't change.
Right.
Yeah.
So then you've already done the exploration. So you've already learned.
What have we learned? How have we learned anything? I'm just curious.
Because you did a bunch of experiments.
Yeah, well, T is 10.
You gave everyone the drugs.
Yeah.
And more people survived from drug 1, so
yeah.
Let's stop giving them drug 2, because that's killing them.
Yeah, but well, think about it this way. What could go wrong? The reward here could be much better. Okay, the reward here, is 100 compared to the mean reward here is 10, right? But after the first 5 goes, this thing here was only 1. It just happened to be negative. I think it was 0. All right. Well, the average here is this average is converging to 10. All right. So this thing here, because of the fact that it's you got unlucky after 10 pulls, this average ended up being, say, 0 or negative. In the meantime, because the mean of this thing is 10, this thing is converging to 10. So if you keep pulling this arm 1, this thing will converge. It'll be consistent. It'll converge to the mean, which is 10. But you're not giving this poor guy a chance. After a few pulls, yeah, sure, he was 0 or the average was negative. But if you just pulled it a few more times, you would have learned, my God, the average of this mean is 100.
Didn't we say big T is very large? So shouldn't we?
There's a little t. It's an online process. What do we do at each stage?
Are we saying that we've already done it a large number of times?
No, we're doing this online. This is state feedback. It's an MDP model. I'd like to be able to choose my action at time t based on observations up to time t. So it's not something, yeah, sure, if I waited till the end, like I waited to the whole year and then I looked, but then what decisions did I make in the meantime? We're trying to decide how to make those decisions.
Right, okay.
Yeah. So this is all online. Right there. Remember this. We're trying to make decisions based on our beliefs and all that, and our observations.
So once you make a deterministic policy, you cannot learn it?
No, we'll find out. Deterministic policies are awesome. You just have to do it right. So this is crap. Absolutely. Yeah, absolutely crap.
So what you're saying is 2 has very high mean, but also high weight.
No, they could. It could be. They both could be small variants. But you could easily still pull it 10 times, even though the mean's 100. You pull it 10 times, and this thing, you're right, variance has an impact. But you won't if you use this policy. That's the whole point. Yeah, with a reasonable probability, you'll only pull arm 2 a finite number of times.
So maybe we should think about the first pull. So you pull 1,
yeah,
and you pull slot 1, and you win $1.
Yeah.
And you think, oh, well, great. You win $1 every time.
Yeah.
And so then you just have your full sponsor.
Because you think $1 is as big as it gets, but you have no basis for thinking $1 is best. Yeah, yeah. The thing is that you have to somehow make sure you pull each arm infinitely often. So you basically, the golden rule is that thing goes to infinity. The number of I explore enough. If we're looking at an asymptotic setting, but forget that. In the long run, we're all dead. What we want is we really want is a lower bound on how many times we pull. This is for asymptotic analysis. Really what we want is something finite, a finite time bounds. So let's leave this Gaussian setting behind. The main reason for putting it in is just to tell you you can apply the LQG problem even in weird situations like this. It's perfectly legitimate to apply the Kalman filter in this setting. The thing is, though, that we don't get much from it, that we have no idea how to use it. Okay. All right. And you would, if we did the calculations, we'd find it basically comes down to this. But if you look at what you'd really like, is you'd like to be able to get, that average payoff at each time step. What people look at is the regret. And we would like to be able to want to minimize that. And basically, there's some beautiful bounds that were obtained by Lai and Robbins. And remember that name, because it'll come up a lot for the rest of the course. You're going to hear Robbins, 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 through the middle of April. And I wish we would say Lai, Lai, Lai through the end of April as well, because all this beautiful work of T. Lai, who's still very active at Stanford. There's just a beautiful paper on this problem from there. And they formulate this regret idea. They give you a beautiful bound, which I had planned to give you. Yes, I will. And then from it, they actually come up with algorithms, both randomized and not. And the bound, I won't give it to you exactly, but I'll give you a rough idea right now. So I can actually give you the constant, which I will in a bit. It's beautiful to know this, because it lets you know how sloppy you can be. Once you know that you can't do anything better than log regret, you can say, well, what kind of policies would give me log regret? And hint, the summation of 1 over n from 1 to t is about log of t. So again, the Gaussian model, you know, it was a little, it introduced a bit of confusion because I had the one-step delay, and there's a Bayesian thing that I have to explain next lecture. But if you go back to this original model, I count up, I look at the total reward that I obtained, you know, whenever I pulled arm A, you know, and I divide by the total times I pulled arm A. You could have this sort of policy. Oh, that should be 1 minus. So again, this is pretty dumb to not use any information here, you know. So I'm going to choose the best, what I think is best so far. So what I call the optimistic policy. Choose the value of A, for which my estimate of the average reward is greater than or equal to all the other estimates, but only do so with probably 1 minus some small number, okay? And with epsilon t, I could do it uniformly and all the rest. Again, that doesn't make much sense. It probably makes more sense to give more emphasis to things that I think are better than others. I might have a weighted, instead of a uniform distribution, I might have a distribution that depends on the, you know, on how good I think something is. But the main point is, if I choose epsilon t appropriately, then I will get, maybe not the optimal constant, but I can get a logarithmic regret. And the epsilon t is, I said it to you. Epsilon t will give log regret. And it's kind of obvious in a way. It's because of the fact that at every instant, I'm going to if you take any of these actions, they get a chance of being hit with probability 1/t times k. So I get a lower bound, I'm sorry, for any action, A. The probability of being chosen is greater equal to 1/t times k. The 1/t comes from the epsilon. You know, it may be A corresponding to a bad bet, you know. And the k really should be k minus 1 because it's uniform on the rest. You know, the uniform distribution on k letters would have mass 1/k at each point. Really, because it's the remainder, let's put it in there to make it clear, minus 1. Okay. And so if I look at the sum, So there it is. So two things come from this approximation. Okay, so two things. So first of all, there's actually two things you can deduce from this. First of all, again, because of the fact that the probability of choosing this arm has this lower bound, when I look at the total number of times, expected number of times I pull an arm A up to time capital T, it's greater or equal to the sum, which is approximately a constant times the log of T. Okay, and that goes to infinity. So I pull every arm infinitely often. All right, but not too often. So bad arms only get pulled. Well, that's the next thing. You can get an approximation that we get almost equality if it's a bad arm. And why do you think that is? You know, well, it comes from this, that because I'm sampling everybody a lot, I'm going to end up sampling the good guy a lot and the bad guys a lot. I mean, my estimate's eventually going to be quite good. Okay. And so it's only the bad guys will be put in the right place, and the good guys will end up here. So you actually get an approximation, you know. And so it says that I sample everybody sufficiently, so this goes to infinity, and I don't sample too much a bad guy, you know, if an action's not the optimal action. And because of the fact that I've got a log there, I only sample a bad guy up to log T times, I get a log regret, which is, again, not the optimal constant, but I get the right number. All right. Okay. So that's one way to do it. I wouldn't do it that way. So there's better ways to do it. We're going to take a break, and I'll tell you how people actually think about this in a way that's more reliable, in the sense of being more practical, lower variance, and easier to analyze. Okay. This is just the easiest thing to describe. Yeah. All right. The one thing that is maybe related to my concern in what you just said is, I'm going to write down this beautiful formula. Oh well, maybe I have to get it from the source. Yeah. Yeah, it's just this unbelievable formula. Okay, so let's just let the average award, if I always pulled action A, you know, my average award would be, you know, T times this. Okay, this is the thing I want to maximize. That's right, I did define it there above. And something that you would have seen if you take a course with me on stochastic methods is relative entropy. This is called relative entropy or Kullback-Leibler divergence. Let's just call it relative entropy. The D is, it's also called divergence, but it's really like a distance. It's not a metric in the sense of it doesn't satisfy the triangle inequality, but it's all sorts of nice properties. And it's positive, it's 0 if and only if these guys are equal, and so forth. It comes up all the time in any problem in learning. It's the foundation of information theory. It's all of channel coding is based on playing around with relative entropy. And it turns out this bound, the constant, and I shouldn't say this. I mean, it's got. I should be careful. Really, what it says is that the log of this implies that line Robbins actually got a finite t-bound. They got really an asymptotic bound. They said the ratio goes to a constant. So I'm putting that in quotes because really they didn't get a finite time bound. They said that if you looked at the ratio for any policy you choose at all, anything you do, the regret divided by log t will be greater equal to this constant. And what does it say? So, if you've got these densities, if these guys are really close together, this is close to 1, then the log of 1 is 0. So this whole thing is close to 0. And you're dividing by this, and so you can end up having a very, very large number here. Okay, and it just so means that the reason for that is you're going to have to do a lot more exploring. You can have two densities that really look close together, but have very different means. That's the problem. It's really easy to think about that. And basically, I can just make the tail a little bit bigger on one side, and just shift things around a bit. I can have very, very different means, even though this relative entropy is the same. And I mean, not the same, but even the relative entropy is small. It's if you take courses of statistical machine learning or information theory, this is the metric by which you say how hard it is to distinguish distributions. If this is small, then it's very, very hard to distinguish whether my observations came from A or A star. Okay, and so it's really reasonable that you'd get this, something that blows up when this gets small. Now, I was so hoping I could give you some insight where this comes from, and I just thought that somebody would come up with a tutorial that was really simple, and I just couldn't find it. So it's way more complicated than I expect. I just don't. I feel like it should be revisited. I bet it's not as hard as it made out to be. When this, when this is done in '85, there were fewer tricks out there. I think that I just haven't found it yet. But so yeah, so that gives you now you have a lower bound. You can actually try to fit the constant. Well, that hasn't quite been done, but people do have nice constants that they've obtained. All right. So So Lai and Robbins did not have that randomized policy. They used something called, well, now it's called a UCB. Well, I'm sorry, upper, not uniform, upper confidence bound. So they didn't call it UCB. I guess somebody at Berkeley did. That's my guess. And actually, my feeling is the computer science community has sort of co-opted this and pretended they invented it in a way. I mean, look at the literature the last week. You've got all these papers that don't even reference Robbins and Lai, and they talk about the upper confidence bound algorithm and reference the CS community, and it's a shame. But it is true that the mathematical CS community has some really cool new results on finite time bounds. And let me just explain to you what this is. So I'm going to write down the algorithm, and then we can talk about it. So here's what they do. They do something very similar to the optimistic policy that you thought of. So this one version. Let's see. What was my notation again? At the T at the bottom of the top. I forgot. Thank you. Okay, so this would be the optimistic policy, which we know doesn't work, because you could get a weird transient and you get locked in, and you'd end up only exploring one arm finitely often. So what you do is you put an extra term, and you'll wonder, why the hell am I doing this? But maybe it'll be obvious. Let's see. And the n, I have a feeling, my notation isn't perfect. And before I came in, I actually wrote down the notation I was planning to use. I don't like that. What was my estimate? My estimate.
R A of t.
No, but it's the estimate. Where's the notation I used for the estimate?
Yeah,
R
hat.
Ah.
R hat. A. Oh, A was A of t. Yeah, in industrial. But it's a big.
I hate my notation. I wish. Yeah. But the trouble is then you're going to see something strange here, because what did I call the number of times I pulled arm A? Oh, is it okay? NA of T? All right, maybe it's all right then. Yeah, well, let's use that. Otherwise it's screwy. I'm sorry about that, but it's okay. I want you to know these concepts. So there aren't any.
NA of T.
Oh, was it good? Good. Now, why would I do this? Now, from a purely mindless point of view, you can see why I do this. With this strange rule, will I pull every arm often enough?
Yes.
And that wasn't a bar, it was a hat, wasn't it?
Yes.
Okay. Now, why is that? So these rewards are all finite. So the average rewards are numbers. They're finite numbers. So these guys are going to be just bounded sequence of numbers, right? If I didn't pull arm A often, only if I pulled it 10 times only, this is 10. Well, that's log t. That ratio will blow up, And so you can see that really you can I'm going to end up pulling each arm about log t steps times.
Plus the difference in the reward.
Yeah, well, I mean, but roughly speaking, I know this term is going to end up being bounded. If this blows up, it means I'm going to be pulling that arm, a lot, which is contradictory to the fact, I mean, yeah, if this blows up, it means I'm pulling the arm a lot, but that means that this is getting big. So, you'll get a contradiction. They can't all do that. So, I mean, anyway, this is going to end up being of that order. Yeah. Yeah. Again, so you can imagine that's it's going to force things to work the right way, right?
The value of gamma is not correct.
Well, gamma equals like 2 in one of the papers. They found the bounds they got gamma equals in the reference I'll send all of you. Gamma equals 2, and in one big paper. And it doesn't quite make sense. You'd think you'd put some more stuff in there about what you've learned and all that. But that's the sort of thing that was in Robbins and Lionel Robbins' paper. And it was chosen. So this is very likely to be larger than right. Oh yeah, less than.
About a star?
No, this is basically the idea is that. So what Lionel Robbins wanted to do is they wanted to come up with, quote unquote, they wanted to come up with something that they knew with high probability would be larger. They wanted to overestimate the means. So basically, they wanted the probability. Think of this as a crappy estimator of the average reward. They're not trying to estimate.
The probability will be small.
And so they want the probability that you don't overestimate the reward, to be small. All right. So they want this. They wanted this thing to be larger than, with high probability, larger than the average reward for each A, okay? But close to the average reward as time gets larger and larger, and and let's see if that makes sense. So what I did is I got rid of the T and stuff. This is basically, I've just pretended I pulled the arm A for the first NA terms. I've sort of rearranged the terms just to make it easy to write things down. You can play around with inequalities here. This is like my R hat. So let's pull this around. It would be so you go and use Chebyshev's inequality. So anybody working this area would say, no, not Chebyshev's, you get a crappy bound, but you get good enough bound where you get the second moment of this divided by that thing squared. And I forgot the square root. Right? Okay, so I'm basically saying I want to say this is an overestimate of the average award, and so I get the expectation of that squared divided by that squared, which is gamma squared times this. And if you work it out, if you remember what the variance is of an estimate like this, it's just like 1 over n. Right? These guys are these individual terms are IID. The reward from arm A time k. They're IID. I'm looking at the variance of an average. And it's just 1 over n a times the variance of each individual term. And yeah.
And why were you doing log of t and not log of n?
Because exactly for the reason I mentioned before, I want to make sure that if this thing remains bounded, the ratio will blow up. Okay. So that I know that I'll pull each arm infinitely often. Okay. All right. So this is what Lyon Robbins proposed in their 85 paper. It wasn't particularly this, but something to ensure something like that. Something to ensure that the probability that the term here exceeded the actual mean decayed to 0 as t goes to infinity. That was the step number 1. Okay, and by choosing it in this particular way, you'll get the log regret bound that you want. And again, I'll send you a paper. You get some really pretty finite t bounds that are just awesome. I mean, absolutely awesome. But I didn't. I mean, it's too much chalk to write it down. But you can get a very, very crisp bound. And you can't, I don't think, with the IID sampling. I mean, why introduce randomness? I mean, really, you're going to get higher variance of your payoff if you randomize. You're much better off something like this. You'd expect a lower variance of your returns with a deterministic strategy.
Of arms, of A's,
of 1. I mean, basically this notation is that it's the reward I get if I pull arm A. Okay, and these guys are IIDs, so I could have put 1 or 2 or 3 or anything. Okay, yeah. So it's just like that. Yeah. So so it goes to 0 as t goes to infinity. That's the only point, is that, anyway, that was their main idea. They said, let's make sure we have all we need is upper estimates that are reasonable. This is going to be consistent, hopefully. Or at least it's going to give you always be an overestimate of the mean, and in the end, Actually, but you actually look at it, it is surprising in a way. It just occurred to me, it does look like a trap. It's not obvious, it's obvious in a way that you can, well, it is obvious that you're going to, if this thing's bounded, obviously this is going to be like this, right? Yeah, but it does look like these could be the same scale, and so you could end up biasing things in the wrong way. If you took gamma to be large, you could get screwed. So in a way, it is surprising this works. You know?
Well, but
yeah.
if gamma just kind of determines your performance. It'll still be the sort of the same end result.
Yeah. No, it's just that, I mean, the uniformity here I think is really important, because all the bad arms are going to be treated the same way, you know, and they're going to, you know, basically end up with the same ratio. But the good arm is going to be treated differently. But the thing is that this will go away. This will become 0. You know, because they'll get pulled a lot more than log t. And so the good arm is going to get an unfair disadvantage, you know, because this term is going to be smaller. So so it is, yeah, it's a bit magic that it works, and I guess it explains why the analysis is so damned hard. I mean, you can't believe how these papers are really difficult.
That's the idea, is you want to disadvantage the good arm.
A little bit, but you don't want to disadvantage them forever. Yeah, this looks like it would disadvantage them forever.
Well, I think you do want to disadvantage, because you have to do the bad arms infinitely often.
Yeah. I see what you're saying, but just imagine. Suppose that all the NAs are log t.
Except for the good arm.
Yeah, I guess it's true that you get a contradiction. That's true. I mean, if yeah, that's true. I mean, no, it's just, it looks circular at first.
I agree.
Yeah.
I also.
Yeah, it's very. Yeah.
Because the good arm's going to get pulled a lot more often.
It's so cute, yeah.
It's going to end up having to be logarithmic.
Yeah.
Because if it goes below logarithmic, then it'll start getting pulled again.
Yeah, it gets pulled a lot, but if it got bigger, if it got really big, then you would be learning a lot better, and you'd learn that it's a crappy, and this would.
It's the difference in the R hat that gives it back the advantage.
Yeah. Yeah, that's right. It's just, yeah.
So you'll have like 2 logarithmic curves, but they'll be like scaled by the RA or something.
Yeah.
Is my interpretation.
Yeah. Huh? Oh, it's fun. Yeah, but yeah, anyway, I'll send you references and you can see for yourselves. And maybe I'll find something clearer. You know, I'd love it if I could. And the only thing that I have to clean up as well is next lecture I got to clarify that model with the Gaussian setting. I just got, my brain was not working when I, wrote that down. I just have to clarify that. But that's really it. And again, you can just see what happens in these cases where you've got learning and optimization going at the same time. You've got specialized tools. Now, if this only worked for bandits, I would not have wasted your time. So this same trick is used, again, for all sorts of similar stochastic control problems with the same flavor. Where you don't, you have, maybe, again, a class of, you don't know which MDP you've got. You've got a stopping time problem where the model is in some class. And so you want to be able to learn and control at the same time. And the same trick is used, exactly, just that. you basically just use exactly the same intuition. So it's, so that's that. Okay, time's up. I will